Okay. So thanks a lot. It's great to be here. Unfortunately online, but I hope it will be fine. So I will be presenting some work on swarm chemistry. So it's kind of similar to what Hiroki said. In my case, it's not chemistry at all, and you will see I'm more a social scientist than a computer scientist, so it's quite far. But I guess we are all interdisciplinary in this community. So yeah, just to present myself, I'm a geographer from IGN in France, and I'm also associate at UCL on the Complex System Institute in Paris. And this work is kind of more methodological on the spatial sensitivity of swarm chemistry. So just to put into a broader context of evolution and the role of space in evolution, so it's quite well known that both spatial structure, so how the species, for example, are distributed in space, but also spatial dynamics, diffusion, and so on, play an important role in evolution. If you think just the islands of Darwin, when he observed two different species of birds, then it's some kind of spatial structure. If you have a spatial segregation, which will induce some evolutionary differences. And if you also think of the niche, evolutionary niche, so the initial definition of a niche is not necessarily spatial, so it's more the parameter space which allows the emergence of the species. But generally, the construction of the niche is linked to spatial effects. And if we can have a look at something closer from the life community, the Holland theory for complex additive systems. So in that context, he proposed spatial boundaries, like the building bricks for model of complex systems. And these boundaries are also linked strongly with a niche. And also, if you look at a biogeography optimization algorithm, they really rely on these different islands exchanging information and evolving to optimize the problems. So now getting closer to the question I study in this work, it's actually based on some recent stream of work that we are developing with with social scientists since a few years. So we started in 2019, mostly with geographers, actually, and also computer scientists, to investigate taking simple social simulation models to investigate how the spatial structure will influence model outputs. So in this paper, we took the shelling model, which is a very simple model of segregation. And we took another one called the Sugarscape, which is like a textbook model. And with these two example models, we showed that if you change the environment, the context in which agents interact, then you will have a very strong change in model outcomes. And it depends, of course, on the model, but for shelling, we had to up 2 times the effect of space compared to model parameters. So we proposed a new workflow for model sensitivity analysis, where we extend the traditional sensitivity analysis to the spatial sensitivity analysis, in which case you need to have some kind of what we call spatial generators. It means that you need to be able to automatically generate spatial configurations. So it's in this direction that then this work went. So we proposed some tools, in particular a library in Scala to generate this kind of configuration. And I presented like also in 2019 an example where we were able to generate urban morphologies with very different properties. So in this case at a large scale. And then the difficult thing is, depending on the type of spatial context and the scale and so on, you have many potential generators of spatial context. Okay. So, but one big question is to what extent this property of being strongly sensitive to space is really specific of the social spatial system, or does it happen in other disciplines. And it's actually very interesting that this morning we had the talk by Seth Bullock. That did something similar. He was changing the network structure, so the spatial organization, and showing that it had a strong effect on agents. So, but it was also a social system because it was an opinion model. So something that concerns us methodologically is to what extent other type of systems. So to what extent do you need space in other type of systems? And actually, the talk by Hiroki just before was also linked to that because they say, okay, we just get rid of space and we have still a very interesting system. So I think it's an open question to what extent. And I also think that artificial life is a very good field because it's interdisciplinary to investigate these questions. So this work is very preliminary, so it's just an extended abstract. It was really testing an idea. And what we did, we took swarm chemistry as kind of a textbook model or iconic model of a life. Regarding this, actually, I remember more than 10 years ago, I was doing my master's, and we had this course, and it was a simulation of complex systems. And the model we had to re-implement for the project was swarm chemistry. So it was already in 2010 or something like this. It was already iconic. So I think it's a really good example, and it shows very interesting pattern of self-organizations. And so we take this model and we consider the evolutionary one, so to be in the context of evolution, and look at how spatial structure will influence evolutionary outcomes in this model. Okay, so maybe I could skip this, but just to give, because everyone knows everything about swarm chemistry in the audience, I guess, but just to give the context. So we have the static swarm chemistry model, which is the basis with the self-propelled particles. So the main parameters are cohesion, element, and separation. These will quite always self-organize into patterns. And then it was modified on longer times to have evolutionary dynamics. So with mutations on particle parameters and transmission when you have collisions. So this transmission is similar to some selection of particles. And since you don't have any fitness function in this context, you can put different rules to transmit parameters values. For example, the faster particle will transmit, the slower one, a local majority, the particle behind the other one, and so on. And it's quite flexible. You can change the rule in space, in time, to foster the evolutionary dynamics. So in Hiroki's papers, what he does is split the space in half, if I remember well. And this half of the space with the rule during a time window, so to put some noise, some contextual noise, and to induce new evolutionary dynamics. So what we do is kind of similar, but really focus on the structure of space and comparing different structure. And the idea is to have so we have a fixed spatial context, but which will be heterogeneous and which we can control. And for this, so in space you will have the rule. So in different regions of the space, you will have the rule applied for the transmission. And we take the rule among a few ones, not all, but a few ones, the faster, slower, behind, majority, and majority relative. And the rule chosen is generated through different spatial generators. So the baseline is just a uniform space, the first one. So here in the picture, the level of gray corresponds to one rule. We have 5 rules, so it's 5 levels of gray. The second one is also kind of a baseline, but it was to see if you have a difference between totally random space and a uniform one. So in the second one, you see this uniform noise. Then the third one is a split of the space. So we have a random x coordinate, random y coordinate, and we split the space in 4. And then we attribute a random rule to each quadrant. So in this case, on the right is the same rule. So it was out of randomness, we have the same rule on the right, but it could be 4 different rules. And the last spatial context, so the last spatial generator we use is kind of more realistic, if we can speak of a realistic in this context, but it's actually inspired from urban systems and for the spatial organization of urban systems. So we consider centers like urban centers. So we have many centers, it's polycentric, and the size of each center is distributed by the scaling law as the flow. So you have a larger one on the bottom, a smaller one, and smaller ones. And yeah. So the idea is to have a kind of hierarchic space and to see if we have a difference between like a very simple split space where you have kind of islands, but the islands are close and they can exchange a lot of particles. And on the right, you have also islands, but segregated islands, smaller. And it's more difficult to exchange. And here, yeah, I didn't say, but the two rules are also taking at random. So these are the different contexts in which we'll run the swarm chemistry. So what are the indicators to quantify outcomes? So we still stay very simple because what would be interesting in that case would be to look at the what also was done in Hiroki's paper, looking at a macro object and looking qualitatively at this type of space, give this type of object. But here it's preliminary work, so we stay with simple indicators. We look at summary statistics on the kinetic parameter of particles, so the averages of C1, C2, C3, and also the standard deviation of these values. And we took also a default standard value for the swarm parameters, except we have quite a small swarm size because we need to simulate a lot of swarms, so it's for a scalability issue. We have a small swarm and a relatively short time, and so we initialize it with a 20 random individual and 180 inactive particles. And the experiment we do is to try to maximize diversity for each spatial context. So in this way, we can have all possible configurations for a given spatial generator. So for this, we use a diversity search algorithm. In this case, we use a PSC algorithm. It's an evolutionary algorithm which does diversity search. So we try to maximize diversity for the summary statistics, and the free parameters are the random seed and the type of spatial generator. So for the implementation of the model, so starting from the open source Java implementation by Hiroki, it was re-implemented in Scala, mostly for practical reasons, because so our library is written in Scala for the spatial structure generator, and it's also easier to integrate into the open world software. So, and it's quite easy to convert Java to rewrite Java in Scala. So it's a new implementation in Scala. So you can check it in this repository. And yes, it's useful because if you don't know the open world software, it's an open source platform in which you can integrate any model. So many different languages which you can integrate as a black box, and even Docker containers, so any model can be integrated. And then you have a lot of different methods, state-of-the-art methods for sensitivity analysis and validation. This includes the calibration with genetic algorithm, global sensitivity analysis, design of experiments, and so on. And also it includes easy access to high-performance computing infrastructure. So if you have a cluster, OpenML will connect your experiment to the cluster quite easily. You don't have to do anything. So it's really a software for numerical experiment. So what do we find in these preliminary results? So this point cloud is the feasible space we obtain. So it's the cloud point of all indicators. So we have 6 dimensions. So I just do a scatter plot to visualize the 6 dimensions. And we also visualize the distribution, statistical distribution among each axis in the diagonal, and also the correlations. So obtained with the PSC algorithm, run for 2000 generations. And so you can never know if the algorithm is totally converged, but when the number of new patterns discovered is very slow, then you can say, okay, it's already fine. I have quite a good coverage of the feasible space. Okay, so we find some interesting correlation, like of course the average of C1 and standard deviation are quite correlated. So if you have a high value of C1, you cannot have a high value of C1. So this kind of cone structure of the first point could. Then also we have also several statistical significant correlations. So it means that you have some structure in a pattern that emerge, but to understand which kind of structure, we should go look in with more detail into qualitative things, which we didn't have time to do. But what is most interesting is do we have a difference between the different type of generators? So in terms of correlations, we have, but also in terms of distributions. So here, for some, it looks like they are totally superposed, but for other, you have small slight difference. So we checked. So we just this spot we cannot say anything, but so we checked statistically if we had some differences, and so we did a t-test to compare each statistical distribution for each generator on each indicator. And among all the possible ones, we find that 4 of them are statistically significant. Of course, so we take a p-value below 0.1, so it's arbitrary. So all the other p-values of pairwise test are above 0.1, but this one are significant. So it means that in this case, you have a strong effect of, statistical significant effect of space. So for the standard deviation of C1, the zips and the uniform are different. And then for C2, the average of C2, uniform is different from split and zip and random zip also. So it means that the average element is a parameter which is the most influenced by the space. Yeah, it's quite surprising, and I don't know how to interpret this. So why do other parameters are less influenced? And beside this,
I think you have less than 2 minutes.
Okay, I'm concluding on the next slide. So thank you. And the flow is a spatial context which has a stronger effect. So it's in all the pairwise comparisons where it comes mostly. And actually, we expected this because it's a more peculiar and particular generator we had compared to the baselines. So this is satisfying. One thing is that if we go back, you see, in terms of statistics, it's significant, but the effect is not very strong. So we should then change the parameters of the generator to see if we can have a stronger effect. But I think it's already interesting as a main result that we have some kind of proof of concept of this spatial sensitivity we found in social simulation models. We found it also in the swarm chemistry model. And I think, so it's not a result here, but I think it should come in more generally in life models. So if you have spatial simulation models, you have some kind of spatial sensitivity. So the next step in this case, we need much more experiments, of course. It's very preliminary to link the type of spatial structure to the typology of swarm which emerge. Also better qualitative understanding of the evolutionary dynamics and the biogeography that emerge. So maybe in the centers you have some type of swarms and between the center of a type of swarms. And then also the type of spatial generator which maybe will be closer to context in which the chemistry will happen. So here it was inspired by other disciplines. But I think in general, this idea of spatial sensitivity is important to look at. And it was very interesting to see Hiroki's talk saying, okay, we remove space, but we still have effect. The difficulty is to separate, in node-generated, to separate the spatial effect from the model effect. And to do this, what you propose is some way to do it. So you average on all the spatial configurations, and then what remains is a model effect, and you have isolated spatial effect. It's actually a fundamental question for geographers in general. So you have the particular and the general, and how to separate the two. Then one open question also, which was raised by reviewers, is how can you apply this to more realistic evolutionary processes? How is it linked to evolution? I don't have any answer to this, but this may be discussed in the future using similar model in ecology maybe. So thank you, and I'm open to questions.